Okay, so today we talk about section 5. Section 5. Orthonormal set. Orthonormal set. So in this section we talk about three concepts. We have three words. Orthogonal set. And another one is orthonormal set. And the last one is orthonormal basis. Orthonormal basis. We have three names. Basis. Orthonormal set. Yeah, orthogonal set, orthonormal set, orthonormal basis. And so first of all, let's see what's the definition. So we have I will give you examples later. So we have several vectors, and here un in Rn, and we have a set, a subspace S. S is the subspace. Of Rn. This is the subspace of Rn. Let me see. Oh, yeah, the number is different. Okay, in Rn space, we have n vectors, and S is the subspace of Rn. So first of all, if we say the n vectors, the set contains these n vectors. If we say it's an orthonormal set, orthogonal set, it means that it satisfies this one. It satisfies this equation. If ui, uj, their inner product equals 0. But when you see ui, uj, all of them are n by 1 vector, it's our ui, it's our uj, it's n by 1 vector. So when we consider the inner product, it also means that consider this vector is transpose, ui transpose. Since ui transpose becomes this one, 1 by n, it's our ui transpose. So it's 1 by n by 1, we can consider their product. So here is defined this way, right? So here, of course, it also means this one. So if ui, uj, these two vectors, ui, uj, their inner product equals 0, then all of ij, for all ij, which is not the same, for different ij, if ui, uj, the inner product equals 0, then we say that this set is orthogonal set. So second one, if it's orthogonal set, and we give more contradiction. What's the more contradiction? I mean, now if you call it the set contains these n vectors, it's not only orthogonal set, it's also normal set. It means that ui, uj, their inner product. Two cases. If I is not equal to j, then it still equals 0. So it still equals 0. But if I equals j is exactly the case. The length of ui is square. I mean, you know that ui, the inner product means ui is length square, right? Okay, so in this case it's 1 if I this one. If I is not equal to j, then inner product equals 0. If I equals j, then the inner product equals 1. So in this case, it also means that its length of ui equals 1. Length of ui equals 1. So in this case, it also means that length of ui equals 1. Length of ui equals 1. And then in this case, if I is not equal to j, the inner product equals 0 means that it's orthogonal set. It's orthogonal set. It means that u1 until un, they are orthogonal. They are orthogonal. So if it's orthogonal set, of course it's an orthogonal set, and all of them has the length 1. All of them has the length 1. So indeed, we could say that by this way. Orthogonal set is exactly equal to orthogonal set of univector, since each of them has the length 1 of univectors. Univectors. Yeah. Orthogonal set of univectors. Orthonormal set is exactly the orthogonal set of univectors. Okay. Yeah, and the last one is about the orthonormal basis. So I will give you example soon. Okay, so u1, u2 until un, if it's orthonormal basis, if it's orthonormal basis of S of the subspace, we have given a subspace of Rn. If we say the set contains from u1 to un is an orthonormal basis of the subspace S, then it means that of course u1, u2 until un is orthonormal set. Just the word orthonormal set, and it's also a basis. Then that's all. I mean, it's orthonormal set. And it's also a basis of S. Is a basis of S. So if dimension S equals n, so if the subspace of Rn, its dimension equals n, then what can we say? Now for this set, we have known that this set is a here, if dimension S equals, then what can we say? Then if we have a set contains n vectors, and it's orthonormal set, then it's exactly orthonormal basis. And the reason is that it's orthonormal set. Then what can we say? It's orthonormal set. So of course, orthonormal set means orthogonal set of univectors. So of course it's orthogonal. They are orthogonal. What does it mean? It means that, for example, here we have ui uj equals 0 if I is not equal to j, right? But our previous result, I mean the result in section 5.1, if we have a set and all of them are orthogonal, then they must be linear independent. If we say the vectors they are linear independent, that means that they are orthogonal. But if they are orthogonal, then it must be linearly independent. Yeah, and you could build just give you a soon quick example to show that here if we have two vectors, they are orthogonal, right? Then how to see that they are linear independent? Okay, so you could do it this way. So we want to show that they are linear independent. So we suppose AU plus BV equals 0. And if we could show that A and B, the coefficient AB must be 0, then it means that U and V they are linearly independent. So and here is assume U and V they are orthogonal, means their inner product equals 0. Then now we want to show they are linearly independent. So suppose it's 0, then we consider their product AU plus BV. So here the vector is 0 vector and any vector it must be 0. The inner product must be 0. But for this one we could separate. Inner product we will separate. So and take out the scalar. So it's A times UV plus B times VV. This one. But now the assumption UV the inner product equals 0. So this term is 0. So we just have this term. B times the length of V equals 0. But here if UV is non-zero, here UV is non-zero. Yeah. The length, if it's orthonormal set, of course, is unit vector. Yeah, so if UV, so it's non-zero. So if it's non-zero, the length is non-zero. So you could figure out B must be 0. So once B equals 0 and the U is non-zero vector, then A must be 0. So indeed we could figure out this one. So in other words, we could know that U and V they are independent. Okay. So follow the similar idea, we could see that orthogonal set it must be linearly independent. So orthogonal set must be linearly independent. So we have, by linear independent, we have n vectors. Linear independent set. And n vectors and it's linear independent, then it must be basis. But it's orthonormal set and its basis, then of course it's orthonormal basis. Okay, orthonormal basis. Okay, and here I could give you some example. Okay, so now let's see some example. So orthogonal set means this one. The inner product of Ui Uj equals 0, and for all I is not equal to j. And orthonormal set means that orthogonal set and their length is 1. It's unit vector. All of them are unit vector. And the orthonormal basis of a set S means that it's orthonormal set in it's also a basis. And if the subspace S its dimension is n, and now we have n vectors, and it's an orthonormal set. Then it must be orthonormal basis. Okay, so now let's see some examples, and we still have one definition for one spatial matrix. For this one spatial matrix is useful in several topics. Yeah, it's useful matrix. Okay, anyway, so let's see some examples. So, for example, 1 0 0 0 1 0. One zero 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 1 0 0 0 1. Okay, we will explain it and later give you. Okay, so first of all, this one. It's a vector in R3. It's a vector in R3. Oh, it's in R3. It's in R3. And here is in R2. It's in R2. Okay, so in R3, it contains two vectors. And once you consider the inner product, it's E to C. It's our U, it's our V. UV is inner product equals 0. 1 times 0 plus 0 times 1 plus 0 times 0 times 0, so it's 0. So UV, the inner product equals 0 means that it's orthonormal set. It's orthonormal set. Right? It's orthonormal set in R3. It's orthonormal set. Sorry, its inner product equals 0 means that it's orthogonal. Sorry, it's orthogonal. Orthogonal. But all of them, their length equals 1, right? So it means that indeed it's also normal set. I mean, of course it's also normal set, but if you just say inner product equals 0, you just know it's orthogonal set. But you see, you could see that their lengths, both of their lengths are 1, so it's also normal set. And in R3 space, now we have 3 vectors, and all of them have length 1. All of them are union vectors. And once you consider the inner product of each two of them, so you will see it's UV, U1, U2, U3. Then you could see UI, Uj equals, if I equals j, then it's just union vector, so it's 1. And if I is not equal to j, then all of them, the inner product equals 0. So in other words, it's also normal set. But also normal set, there are 3 vectors in R3 space. So originally we just know it's also normal set in R3. But it has 3 vectors, so it's also orthonormal basis. Orthonormal basis in R3. Orthonormal basis in R3. And now let's see this example. First of all, we could check they are orthogonal or not. So it's our U1, U2. So we check their inner product U1, U2. U1, U2, their inner product is equal to U2, U1, their inner product. Right? It's equal to this one. So we just need to consider this one is a norm. And here, U1, U2 is a inner product equals 1 times 1 plus 1 times -1. So it's 1, -1, so it's 0. So it means that indeed they are orthogonal. So it's orthogonal set. These 2 vectors, U1, U2 are orthogonal. It's orthogonal set. But what's their length? If you see U1 is length. The length is What's this? It's divided by this way. Their inner product, and you should consider is square root. Square root. So u1 is it means square root of inner product means 1 square plus 1 square. But you can square root, so it's exactly square root of 2. Square root of 2. And the u2 is u2 the inner product. So and consider it square root. So again, it's equal to 1 square plus negative 1 square. But it's still equal to square root of 2. It's still equal to square root of 2. Okay, so in this case, each of them is square root of 2, so it's not univector. So it's orthogonal set, but not orthonormal set. Not orthonormal set of R2. Okay, but not orthonormal set. Not also, here it's orthogonal, but it's not orthonormal. Not orthonormal. Since it's not univector, each of them is not univector. But for these two vectors, if we want to, for this vector u1, for this vector u2, if we want to multiply by some scalar on u1 and multiply some scalar on u2 to derive orthonormal set, then what should we multiply by? What should we multiply by? For this vector u1, its length is square root of 2. So if we divide by square root of 2, if we consider square root of 1 over square root of 2 times u1, I mean, actually we consider the vector for 1 over square root of 2 times u1 and 1 over square root of 2 times u2. These two vectors. Then you will see the length becomes 1. The length becomes 1. So it becomes univector. Okay, so actually if we consider this one, divide by square root of 2, so it's 1 over square root of 2, 1 over square root of 2, and 1 over square root of 2, negative 1 over square root of 2. If we consider this set, then you could see that. First of all, for this vector, if you compare with these two vectors, we just multiply by square root of 1 over square root of 2 on this vector, and then for this one, we just multiply by 1 over square root of 2 in this vector, right? So for this property, u1, u2, their inner product. For this property, u1, u2, their inner product. I should denote it by, here is if we denote by w1, w2, w1, w2. So of course w1, w2, the inner product must be 0, right? If you check inner product, you could see that indeed it's 0. Otherwise, you also could see that it's exactly w1 is 1 over square root of 2, 1 over square root of 2 u1, 1 over square root of 2 u2. Right? So we could tell the scalar, so it's 1 half. Hence u1 is inner product. But this part is 0. So it's still 0. Okay. Anyway, so originally they are orthogonal, and we multiply by some scalar in this vector, you also could see that it's still orthogonal. And the second one is orthogonal, but if we want to know it's orthonormal set or not, we should check it's univector or not, right? So W1 is length. It's easy to see. Its length is square root of 1 over square root of 2 is square, plus 1 over square root of 2 is square. So indeed it's 1. And if you see W2 is length, you also could see that it's 1 over square root of 2 plus negative 1 over square root of 2 is square. So also equal to 1. Yeah, this part probably you could not see very well, but it's fine. Otherwise I could write in this way. W2 is equal to 1 over square root of 2 is square plus negative 1 over square root of 2 is square. So it's still equal to 1. Right? It's still equal to 1. So what can we say? Indeed, it's so indeed W1, W2, I mean 1 over square root of 2, 1 over square root of 2, 1 over square root of 2, negative 1 over square root of 2. It's also normal. Set in R2. And in R2 space, dimension 2, we have 2 vectors, and it's also normal set. Then it means that it's also normal basis. Also normal basis of R2. Since we have 2 vectors in R2 space, and it's also normal set, then follow the previous result, we could see that it's also normal basis. It's also normal basis. Okay. Yeah. And for the orthonormal basis, if you want to, in this section, you should know if I give you a set contain several vectors, you should know it's an orthonormal set, orthogonal set, orthonormal basis or not. Okay? And if it's orthogonal, it's not orthonormal set, then what can we do? Or actually, of course, we could just divide by, probably we could just divide by its length. Divide by its length, then originally it's orthogonal set, then it becomes orthonormal set. I mean, in this example, you could see that if we have U1, U2 until UN, and it's orthogonal set, orthogonal set, and how to get orthonormal set? You could divide by its length. UN divided by its length. Then it's also normal set. It's also normal set. Right? And it's actually exactly our first result. I mean, note. And orthogonal set. U1 until UN can be changed to orthonormal set. Orthonormal set. Which one? This one. Just divide by its length. Okay, just divide by its length, and we can get orthonormal set. And yeah, but if we just have linear independent set, not also, as we say, orthogonal set is linear independent. It's not. But orthogonal set is linear independent, and linear independent set is not orthogonal set, right? And so if we just have linear independent set, we want to figure out orthogonal set, then we should use the result in next section. It's the last section in chapter 5. To get the orthogonal set and divide by its length to get orthonormal set. It's what we want. In next section. Okay. Anyway, so it's the first one, and the second one is that for this example, you could see that. I mean, we will define I will give you a spatial matrix. Its definition, and give you a name for this kind of spatial matrix. And if you want to check a set, it's orthogonal set or orthonormal set or not, you could just check it by another way to check it. Okay, so we have in this, yeah. So now we have 2 vectors U1, U2 in R2 space. So now we consider Q, the matrix Q. So for the matrix Q, we define it by this way. The first column we consider U1, second column we consider U2. So the matrix Q is it's 2 by 2 matrix. So it's 2 by 2 matrix. So it's 2 by 2 matrix. And now, what's the matrix Q transpose? The matrix Q transpose is exactly, so U1 is the first column, and its transpose becomes fourth row. I mean U1 transpose is the fourth row. U1 transpose is the fourth row. I will give you the example, and the U2 transpose is the second row. U2 transpose is the second row. Yeah. It's Q transpose. Yeah, and another one I write down here. Yeah, you see. So Q transpose. So Q transpose is exactly Q transpose Q. What's the product of Q transpose Q? Q transpose Q is, here is U1 transpose in the first row, U2 transpose in the second row. Right? And Q is first column in here and the second column here, this one. So when you consider Q1, Q transpose Q, what's this? What's this? It's probably the result, the property is section 1.6, the last section in chapter 1. I mean, it's 2 by 2, it's 2 by 2. When we consider their product, first row, first column, and first row, first column in, yeah, here, for example, is the first row, for example, is the vector 1, 2, and the U1 is the vector 1, 2, right? 1, 2. U1 is the vector 1, 2, then it becomes 1 square plus 2 square, but you also could write in this way. Just write it down. Just put this one over here. I mean, just consider this one. U1 transpose U2. That's U2. So just write down this one. U1 transpose U2. U1, sorry, U1. Since it's 2 by 1, it's 1 by 2. It's 2 by 1, it's 1 by 2. So it becomes 1 by 1 scalar. And here, 2 by 1, 1 by 2, so it's still, sorry, it's, oh, sorry, something wrong, 1 by 2. Sorry, 1 by 2, 1 by 2, 2 by 1, 2 by 1. So it becomes 1 by 1. And here is still 1 by 1, but it's U1 transpose U2. U2 transpose U1. U2 transpose U2. This one. This one. So it's equal to this one. So I mean, when you consider Q transpose Q, their product is this one. And of course, this form you also could write in this way. U1 transpose U1 is exactly their inner product. U2 transpose U2 is exactly their inner product. U1 transpose U2 is exactly U1 U2 inner product. U2 transpose U2 1 is U2 U1 is inner product. Actually, they are the same. They are the same. It's the matrix. Q transpose Q is exactly the matrix. It's exactly the matrix. Okay, so if we say these two vectors U1, U2, these two vectors U1, U2, if we say they are also orthogonal same, if we say they are orthogonal same, what does it mean? If orthogonal same means that Uij equals 0 if I is not equal to j. So it means that U1, U2 equals 0. But U2, U1 is the same. It's the same. If both of them have the same scalar. So in this case, it means that these two values, if it's if the entry if it's the entry which is not in the diagonal entry, then it should be 0. Not in diagonal, then it should be 0. So in this case, Q transpose Q, it just have non-zero entry in diagonal entry, probably. So Q transpose Q, it should be diagonal matrix. It should be diagonal matrix. Diagonal matrix. So U1, U2, these two vectors, they are orthogonal set. Means that Q transpose Q is a diagonal matrix. Q transpose Q is a diagonal matrix. And moreover, if U1, U2, they are orthonormal set. Orthonormal set. Orthonormal set means that it's just not orthogonal set. All of their lengths should be 1. All of their lengths should be 1. So here we have U1, Uj, U1, U2 is equal to U2, U1 that is equal to 0. But the length of U1 and the length of U2, of course, length is the square root of U1 and the U1 the inner product. But I write down in this way: U1, U2 equals 0, equals 1, equals 1. But here it means the U1, the length is square. The length is square. The length is square. Okay. Yeah. So in this case, you could see that if they are orthonormal set, means that off diagonal entries are 0, and in diagonal entries are 1. Diagonal entries 1 is square is also equal to 1. So it means that Q transpose Q equals diagonal entries is 1. 2 by 2 matrix. So we could write in this way: 1, 1 by 0, 0. It's this one. It's this one. So it's identity. So it's identity I2, identity. Okay. So orthogonal set means that Q transpose Q equals diagonal matrix. Is a diagonal matrix. And if it's orthonormal set, means that Q transpose Q is identity. And then we have two vectors in R2 space. So in this case, it also means that U1, U2 they are orthonormal basis. Orthonormal basis of R2. Of R2 in this case. Okay. Yeah. So here just 2 by 2 case, but even for n by n is the same. N by n is the same. So I write down the n by n result. It's the same. Just explain it by 2 by 2 matrix. But even for general case, n by n is the same. So I write down the result. We have the series U1, U2, and here UN in N. So you should know how to put a matrix. Our matrix Q, we put it in this way. Here all of them are n by 1. N means that it's n by 1, n by 1, n by 1, n by 1, n by 1. So we consider a matrix Q. So first column we consider U1, second column U2, and here UN, and here UN. So in our n space, in our n space we have n vectors. So in this case is we have n vectors in our n. So it's n. So it's n by n matrix. And our result is that if these n vectors is orthonormal set, orthogonal set. Sorry, orthogonal set. These n vectors are orthogonal set. Orthogonal set. It means that Q transpose Q is like this one. Off diagonal entries are 0. Off diagonal entries are zeros. So it must be diagonal matrix. So it means that it's diagonal matrix. It is diagonal matrix. Second one. And if it's also normal set, then Q transpose Q. Diagonal entry should be 1. So in other words, it's identity. It's identity. In other words, it's identity. It's identity. Okay. And in this case, we also call it orthogonal matrix. Orthogonal matrix. I mean, if it's for this matrix Q, in particular, if let me see how to, yeah, okay. Also normal set if and only if this one, but in general, if n equals n, then we call this matrix. Then we call if n equals n, Q. The matrix Q originally is n by n, but now Q is n by n matrix. Q is n by n matrix. And this n by n matrix satisfies this one. Q is called orthogonal matrix. If we satisfy Q transpose Q equals identity. So in other words, in this case, Q is called orthogonal matrix. If n equals n. Okay, so if n equals n, it's the definition. It's the definition. Here is the definition. Here is the definition. It's the definition. Okay, so if n equals n, then Q is n by n is square matrix. And for this square matrix, if we satisfy this one, Q transpose Q equals identity, then we call the matrix Q is also orthogonal matrix. In other words, if we have n vectors in n space, and we consider the matrix Q, then if we want to show its orthonormal set for these n vectors in n space, we want to show its orthonormal set, we could show this one, or you could say it exactly means that Q is also orthogonal matrix. Yeah, orthogonal matrix. Yeah, and I give you the examples. And here, so orthogonal matrix means this one. But here, I want to remind you. So orthogonal matrix means it satisfies this one. Q transpose Q equals identity. But in this example, you could see that once you consider determinant of Q transpose Q equals determinant in, determinant in equals 1, so it's non-zero. And their determinant equals, we could separate determinant Q transpose times determinant Q. So you could see that all of them are non-zero. And and its determinant non-zero means that Q is immutable. Q is immutable. And actually, Q times another matrix. This matrix Q transpose times Q equals identity. It also means this matrix is immutable. It's immutable, and it's Q. This matrix Q is inverse is exactly Q transpose, and the Q inverse is exactly Q transpose. For this one, yeah. If it's so orthogonal matrix Q, for the orthogonal matrix Q, its inverse is exactly its transpose. So for the orthogonal, so Q, if Q is n by n, Q is orthogonal matrix, then originally it means this one, but we could know that indeed Q transpose is exactly its inverse. Q transpose is exactly its inverse. Okay, so finally I just give you several examples and we finish this section. Several examples and we finish this section. Yeah. So first one, for example, we have 1, 1, 1, negative 1. And second one, cosine theta, sine theta, sine theta, negative cosine theta. Cosine theta, sine theta, sine theta, negative cosine. Or you could let sine be here. That's fine. Just choose one of them be negative. Okay, yeah. So in this case, if we want to show they are also orthogonal or orthonormal, then we could use the result to show that. And we have to, actually, all of them are in R2 space. So once we could show that they are orthonormal set, it also means that they are orthonormal basis. Our goal is to show it's orthonormal. Let's see the difference. Okay, so now let Q, here is our Q. So Q we consider is our U1, U2. So 1, 1, 1, negative 1. The Q transpose is the same. I mean transpose is, but for this one is symmetric. So first current becomes first row, second current becomes second row. It's the same. So Q transpose Q, once you check it, Q transpose Q is 1 plus 1. 1 here, and 1 subtract 1. And here 1 times 1 plus negative 1 times 1. So 1 subtract 1. And still 1 plus negative 1 times negative 1, so it's plus 1, this one, and it's 0, 0, so it's 2, 0, 0, 2, so it's diagonal. So Q transpose Q is exactly diagonal matrix, so we could see that indeed these two vectors are orthogonal. Of course, you could say that just consider the inner product, right? Just consider the inner product. U1, U2, the inner product equals 1 subtract 1 is 0, and it's also this one, also equals 0. So we could get this one, right? So of course, for this one, you could follow the definition to say that they are orthogonal set, or use the matrix Q to show Q transpose Q is diagonal, and we could use the. And we could know that actually they are equivalent. And this one is the same. You could say that we just denote it by U3, U4. Then U3, U4, their inner product equals cosine theta times negative sine theta, so negative sine cosine, plus sine times cosine. Here originally is cosine sine. This one is the same, cosine sine, plus sine cosine. But it's the same, so it's 0. And it's also equal to U4, U3, their inner product. So in this case, you could see that they are orthogonal. And to check their length, so first of all is this one. Second one, to check their length, U3 is length. Square root of cosine square plus sine square. Right? And the cosine square plus sine square is 1. It's 1, so it's 1. And the U3, U4 is not its length. Its length is negative sine square plus cosine square. And it still equals 1. And 1 is square root is also equals 1. So the inner product is 0 if I equals if U3 equals not is not equal to U4. And all of their length is 1. So indeed they are also orthonormal set. Right? So indeed they are orthonormal set. And if we have two vectors in R2, so indeed it's orthonormal basis of R2. And we still have another way, let Q be U3, U4. So it's cosine theta, sine theta, negative sine theta, cosine theta. I mean, we have two ways to derive this result. It's our U3, U4. And the Q transpose is exactly cosine, negative sine, sine, cosine. Sine, cosine. So now, our result is that if we want to show its orthonormal set, we should show that Q transpose Q is identity, right? Q transpose Q is identity. So now let's see Q transpose Q. Q transpose Q is exactly Q transpose Q. Q transpose Q. So cosine square plus sine square. And this position is cosine negative sine, negative cosine sine, plus sine cosine, sine cosine. And here is negative sine times cosine, negative sine times cosine, plus cosine times sine. And here is negative sine times negative sine, so it's negative sine is square, plus cosine is square. This one. But this 10 is 0. This 10 is 0, this 10 is 1, this 10 is negative sine square is also sine square. Sine square plus cosine square is also equal to 1. So indeed, it's identity. It's 1, 0, 0, 1. So it's identity. So indeed, U3, U4, these two vectors are orthonormal basis. Originally we know that it's orthonormal set in R2, but two vectors, so of course it's also orthonormal basis of R2. Okay, of R2. Yeah, okay. Okay, so I give you just one more example, then we finish it. Just one more example, then we finish it. So we still can consider, if we consider square root of 3 over 2, 1/2, negative 1/2, square root of 2, this one, these two vectors. Okay, we consider these two vectors, and we want to show its orthonormal basis or not orthonormal basis of R2. We want to show this one, to show its orthonormal basis of R2. Yeah. So of course you could use this way, the first one, or it's our first way, and it's our second way to show it. So here I consider, if I consider second way check our result again. So you can see the matrix Q is our U1, U2. So it's a square root of 3 over 2, 1 half, negative 1 half, square root of 3 over 2. So our transpose, Q transpose is exactly, it's transpose, so it's square root of 3 over 2, so it's negative 1 half, and then 1 half, and the square root of 3 over 2, this one. And once you consider Q transpose Q, what will you get? Q transpose Q, I circle E, you will better to know how to compute. Okay, so it's 3 over 4 plus 1 over 4 in the first position, and negative square root of 4, negative square root of 4 plus square root of 4 plus square root of 3 over 4 over 4. And here negative 1 half times square root of 3 over 2, so it's negative square root of 3 over 4 and plus square root of 3 over 4, and the last one negative 1 half, negative 1 is 1 over 4 plus 3 over 4. So if you check it, it's 0, it's 0, it's 1, it's 1. So indeed it's identity. Indeed it's identity. So indeed we could know that it's also normal set, and it's exactly also normal basis. Okay, so of course you also could use this way to check to check U1, U2 is inner product equals 0, and U1, U2 all of their length is 1. All of their length is 1. You also could check it by this way. Yeah. Okay. Yeah. So I think it's all the result in this section. So finally, I write down the homework in this section. So the homework in this section 5.5. It's 1, 2A, 4A, 21. Actually, for this section, you should know the definition about also orthogonal set, orthonormal set, orthonormal basis, orthogonal matrix, and how to explain this one. Okay, that's all.